What we're going to do here is finally talk about the capacitor and the impedance of a capacitor in the phasor domain. In the last section, we talked about resistors, and we talked about inductors, and we basically boiled it down and said that the impedance is an analog to the concept of resistance when we're talking about AC circuits. So ultimately, when you solve your circuits, all of your components, your resistors, your capacitors, your inductors, you're going to transform them to the phasor domain. The resistors will stay the same. The inductors, you'll convert to the impedance we talked about in the last section. The capacitors, we're going to talk about its impedance here. Once you know how to convert all the circuit components, we've already talked about how to convert the sources to phasors, then you can actually do some analysis. So we're kind of walking through here. So I'm going to show you what the impedance is for a capacitor, and then at the end I kind of want to wrap up impedance in general, and in the next section we'll work on some impedance problems to give you a little bit of practice. It is a little bit of a weird concept at first, but you'll find how useful it is in a second. So for capacitors, right, capacitors, right, for capacitors, the important relationship really is that I is equal to C dV dt. So for inductors, we had a similar relationship between the current and the voltage involving a derivative. For capacitors, we have a very analogous relationship where the current is equal to the derivative of the voltage and multiplied by a constant here. So again, we expect the current and the voltage to be shifted with respect to one another, kind of like it was for inductors, because we have this derivative here. And so let's draw a graph and sort of learn from that, and we'll tie that all together. So if this is time, let's draw, since we have the derivative on the voltage, let's draw the voltage first in red. Let's just say that the voltage starts at the origin and goes up like this. It's all arbitrary, remember, because all I care about is showing you the relationship between the two. So whether I start the voltage at here, or I start the voltage here, start the voltage down here, it doesn't matter. All I want you to do is see how the current and the voltage look with respect to one another. So this is the voltage. Let's just say we're driving a capacitor with a voltage that looks like this. How does the capacitor respond, for lack of a better word? What is the current through the capacitor going to look like? Well, at every point in time, it's the derivative of the voltage. So we expect, because the curve is changing greatest up here, we expect to start here, and I'll draw myself some tick marks in other locations to help me draw the thing as well. So we expect the current to start up here and drop through the axis here and go way negative like this, and then go through here, reach a peak here, go back down through here, reach a peak there, go up there, let me go a little bit higher, like this, and then come back down, and so on. So it's not perfect, but you can see what's going on here. So at every point when the original voltage curve is changing most rapidly here, we get a peak. Here, we're changing rapidly here, so we get a peak. We're changing rapidly here, we get a peak. We're changing rapidly here, we get a peak, and so on. The reason I'm drawing the blue curve bigger is to help you visualize the difference, but the value of this capacitor could be such that on the scale, it might stretch it like this, because we're basically taking the derivative, multiplying by something to get the current. All right. Now also notice that everywhere where the voltage was a maximum here, we get a current of 0, because when the voltage is not changing very much, the current is 0. So here we have a 0, here we have a 0, here we have a 0, and so on. So it's very, very similar. Let me draw this guy. It's very, very similar to the situation we had with an inductor, with one important difference. Notice that in this case, the peak of the current comes before the peak of the voltage. The peak of the current comes before the peak of the voltage. So we say that the current leads the voltage. In a capacitor by, same thing, 90 degrees. It's always a 90-degree shift. The reason it's a 90-degree shift is because this is just a derivative, and we know from the properties of the cosine or the sine function that whenever we look at the first derivative, sine is going to change into a cosine and so on, that those are shifted with respect to one another on this axis here by 90 degrees. All right, by 90 degrees. So we can say the same thing is true. Current leads, or we could say voltage lags the current by 90 degrees. Now, these look very, very similar, but I do want to show you the difference. Notice here that the blue curve, the current, don't look at it in terms of blue and red, look at it in terms of current and voltage. In this case, the capacitor, the current leads by 90 degrees here. Notice over here, the current is I, the current lags the other direction by 90 degrees. Let me say that one more time, it's important. Think about the voltage here. So don't look at red and blue, just look at in terms of the voltage here and what the current is doing in relation to it. And for a capacitor, the current is to the left. Over here, if this is the voltage, the current is to the right. So what it's basically saying is for the capacitor relationship, the voltage and current is shifted one direction by 90 degrees, but in the inductor relationship, the current and voltage is also shifted by 90 degrees, but in the other direction, right? So one way is shifted this way, one way is shifted this way. So you can see that capacitors and inductors, something we talked about for so long, are just like mathematical cousins of one another. One deals with the magnetic field, one deals with the electric field. One has a shift one direction by 90 degrees, voltage and current. One has a shift the other direction by 90 degrees, voltage and current. That's going to be important in a minute, so keep that in mind. So let me cut to the chase on what you really want to know, which is the impedance of a capacitor. I'm going to give it to you. I'm not going to prove it, just like I didn't prove it before. But I want you to really understand it. So we already discussed in the last section, I'll repeat it for you here, that Ohm's law basically applies. So V is equal to I times Z. This is the phasor voltage, which is a complex number. This is the phasor current, which is a complex number, times some impedance that's dealing with this capacitor. So the impedance of a capacitor, actually let me scoot this over to the left a little bit. Okay? The impedance of the capacitor is equal to 1 over j omega c. 1 over j omega c. So notice the duality. The impedance of the capacitor, 1 over j omega c. The impedance of an inductor is just simply j omega l. There's no 1 over, but the j omega l looks a whole lot like the j omega c over here. So basically, whatever the capacitor value is in farads, you put it in here. Whatever the frequency is you're driving at, you put it in there. Now notice that the impedance of the capacitor is going to depend on the value of the capacitance, obviously, and the impedance of the capacitor is going to depend on the frequency as well. So if you think about how capacitors are constructed, they're basically just two plates and they don't touch. There's a dielectric in between, right? So if you drive it with a DC source, with a source that doesn't change, like 5-volt battery or something, just constant 5-volt battery, with a frequency of 0. If you put a 0 in here, 1 over 0 is going to give you infinity, which means infinity ohms, which is an open circuit, right? So it makes sense. When you look at the limiting case, whenever it is basically not oscillating at all, it's an open circuit. There's nothing between those two plates. So if there's nothing changing, then this guy gets to infinity ohms because the units of impedance is always ohms, right? They start increasing that frequency, then the impedance, will come down from infinity. If you go to infinity, driving it with infinity frequency super, super fast, the impedance comes down to 0 if you could drive it with infinity radians per second. Of course, you can never do that, but that would be what you would do. So the unit of this is ohms, and I'm going to circle this. Right? But I also want to show you something. Even as I circle it, this is the equation I use, but I want to manipulate it just a little bit and show you something. So let me go ahead and put an equal sign over here. Notice that the j is on the bottom. That's fine. There's nothing wrong with that. But what if I wanted to move the j onto the top? What if I wanted to? How could I do that? Right? So this gets into getting practice with complex numbers. It's not quite obvious how you do it. But what you can do, I'll just show you, 1 over j omega c. Remember, you can multiply a fraction, any fraction, by anything you want as long as you multiply top and bottom by the same number. I can take the fraction 4/5 and multiply by 10 over 10. That's fine, as long as I do it to the top and to the bottom. So here I'm going to choose to multiply this fraction by j over j, which is just the imaginary number divided by the imaginary number. Now on the top, I'm going to get j, and on the bottom, when you think about it, I'm going to get j squared. Remember, we said j squared was always -1. So it's going to be negative omega c. So really when you do this, what you get is you get j you get negative j over omega c. So if you wanted the j to be in the top, this is an equivalent way to write the impedance. If you want to say j over negative omega c, you could do that. Typically, you write it in books as 1 over j omega c, but this is an equivalent way to write it. It's going to give you exactly the same thing. But notice, back before, I told you, I gave you a definition. I said, here's the impedance of an inductor. Here's the inductive reactance. You just take away the j, and whatever's left over, we call it inductive reactance. It's just a number without the complex part of it. It's just representing the impedance of the thing, but without the actual imaginary number there. So now that we have written the impedance of a capacitor with j on the top and with this stuff on the bottom, what I can do is I can just take the coefficient of the j, and I can say that the capacitive reactance is equal to, the reactance is always equal to the impedance, but with the j gone. So it's negative 1 over omega times c. So you might need to see that on a test. I mean, sometimes your professor might say, the capacitive reactance is this, and you're going to need to put it in with into an impedance, because when you're dealing with circuits, your capacitors and your inductors always have to have complex numbers with them if you're dealing in the phasor domain. So almost always you're going to be dealing with impedance with a j when we're doing all of our circuit analysis, but occasionally you might try to be tricked on a test and they give you the reactance. And you'll need to know that all you have to do is put a j in front of it to make it the impedance. Just like for an inductor, all you have to do is put a j in front of this to make it the impedance. All right, so big picture. Now we know what the concept of impedance is. It's the same thing for resistance, right? For resistors, it's just ohms. It's just 50 ohms or whatever. It's a real number for resistors. For capacitors and inductors, the impedance represents how much the current is resisted, just like it does for resistors, but they're always going to be imaginary numbers. The value of the impedance is going to depend on the value of the capacitor or the value of the inductor, but it's also going to depend on the frequency. So if you start changing the frequency, the impedance of their whole circuit changes. That's kind of a wacky concept to think about. So you might want to think about that for a second, because that's different than anything we've done before. You know, with resistors, you build the circuit, it's always the same. But you could build a circuit with capacitors and inductors, and the circuit will behave completely differently at different frequencies, because the impedance of the capacitor is going to be different at different frequencies, and the impedance of the inductor is going to be different at different frequencies. All right? Now, the last thing I want to show you is, or tell you, is just kind of something in passing. I'm not going to use this as a rigorous proof, but I want to at least bring it up to you to give you a little bit of enrichment. I think we've covered the bulk of really what I wanted to talk about here, but I want to give you a little bit of enrichment. I did not derive this equation for the impedance of a capacitor. I did not derive the equation of the impedance of an inductor. I didn't derive that because I didn't think it was worth it. But I do want to illustrate something for you. Let me draw, remember we did this before, let me draw the complex plane. This is what we call the complex plane. It looks just like an XY plane from geometry or algebra. In fact, it is really the same concept, except when you talk about the complex plane, instead of the x-axis, you say this is the real axis, and you say this is the imaginary axis. You can think of it as x comma y, except when you're talking about complex numbers, you think of it as real comma imaginary. So every complex number, remember complex has a real and imaginary part, you can plot it on this graph, right? So all the real numbers that you've ever seen in your whole life, -1, because those are real numbers, -2, +3, 10.4, 20.5, all of the real numbers really just lie on the number line. This is the same number line you learned about in 3rd grade and 4th grade, but now I'm expanding it. I'm telling you there's another number line that lies perpendicular to it. We call it the imaginary number line. All the imaginary numbers that you ever knew, 3j, or if you're thinking about I, 3i, 4i, 10j, I and j are the same thing in electrical engineering, right? They all lie along this guy. These are the positive imaginary numbers, these are the negative imaginary numbers. So all the real numbers are here, all the imaginary numbers are here. And when you have a complex number, it has a real part and an imaginary part. So a complex number might be here, or here, or here, or here, because it has a real part and an imaginary part. And you might say, why am I telling you all these things? I'm telling you this because of the following, and I think you'll be interested in this. all of the resistors that we've ever studied, resistors, remember those things we talked about all the way up before AC analysis, 35 ohm resistor, 10 ohm resistor, 4 ohm resistor, those things, those are all real numbers. So the resistors are all real numbers, and they're all positive. So this is resistors. They're all real and they're all positive. So the value of the resistors are all along the blue line, right? They're real numbers. But when you look back to inductors, now that we've studied inductors enough, the inductive impedance, all right, in terms of ohms, is j omega L. This is purely an imaginary number. It's just a j. There's no real part to it. It's just a j, and this multiplied together just gives you a number. So the impedance of an inductor might be 8j, or 6j, or 3j, whatever. It's a number times j, or a number times I, however you want to think about it. All right? So that means that all of the inductive impedances are always up here. Right? So this is inductor. They lie all along the imaginary axis up here, right? Notice for the capacitive impedance, it's 1 over j omega c, which I showed you through a sequence of simplifications, is the same thing as negative j over omega c. So that means that since omega, the frequency, is always positive, and the capacitance c is always positive, and you always have a negative sign out here, that the when you start doing your problems, you'll see it over and over again as well. The impedance of capacitors is always going to be negative j times something, always. Negative j with something that you get from omega c. So the typical impedance you might see of a capacitor might be negative 3j, negative 4j, negative 5j. It's always negative, never positive for capacitive, always negative. You can see that with the sign there. So what I'm trying to point out to you here is, let me use this guy here, that the capacitors are always down here, negative imaginary. So this is capacitor. All right, now you might ask, why is he writing all these things? This doesn't make any sense at all. I'm going to hopefully blow your mind. If I don't blow your mind, maybe you don't understand what I'm trying to say, but I'm trying to give you a little bit of motivation, a little bit here, and a little bit of big picture of what we've actually done by using these techniques. I didn't prove to you that this is the inductance, I'm sorry, the impedance for a capacitor. I didn't prove to you that that's the impedance of an inductor. I just gave it to you as fact. And the first thing I thought whenever somebody told me that the impedance of an inductor was always imaginary, I was like, why? How does imaginary number have to do with any of it? It's a real coil, it's a real wire, and it's got real voltage and current. Why is it imaginary? And why is the impedance of a capacitor imaginary? It doesn't make any sense to me intuitively, but here's where we're going to tie it together. Notice, when we go way back, the relationship between voltage and current as far as resistor is always in phase. They're always in lockstep. The phase angle is 0 between voltage and current, all right? That is why resistors always lie along the real axis, because if you think about this in terms of a unit circle, that's what I want you to do now. Think about this in terms of a unit circle, where this is 0 degrees, and you go around to pi over 2, 2 pi over 2, 3 pi over 2, and then you get back around to 2 pi or 0. The resistors are always here, which is, think of it as 0 degrees. Notice there's a 0 degrees between voltage and current, right? But then we get to inductors. We get to inductors, which are actually right here. We get to inductors right here. We said the voltage leads the current by 90 degrees. The voltage leads the current by 90 degrees. Okay? So notice we're up here. The angle between here and here is 90 degrees. And when the voltage leads the current, we say it's like a positive angle there, right? So I guess what I'm trying to say is when you compare inductors to resistors, you can see that the shift between the voltage and current is 90 degrees. For resistors, they line up perfectly, but for inductors, they're shifted 90 degrees. Notice that all inductors are J times something. So the shift between a resistor and an inductor is shifted in the complex plane by 90 degrees. In a similar way, the two graphs are shifted by 90 degrees. And when you look at a capacitor, you see that it's always negative J omega divided divided by omega c. That's the impedance of a capacitor. And all of the capacitors lie down here. And when you look at the graph of a capacitor, the voltage current relationship is also shifted by 90 degrees, but in the other direction. That's the key part of it. When you look at the shift here and the shift here, we already talked about, they're in a different direction than this. So inductors are shifted voltage and current 90 degrees one direction, and capacitors are shifted with the voltage and current relative to themselves in the other direction. So capacitors are 90 degrees, or I should say 90 degrees negative from where resistors are, and inductors are shifted sort of 90 degrees positive from where they are. So that's kind of why it makes a little bit of sense, even though I'm not proving it to you, it makes a little bit of sense that inductors are pure imaginary, because the voltage current relationship is shifted 90 degrees, which is exactly what is represented here, 90 degrees in the complex domain. Capacitors, the voltage and current also shifted 90 degrees the other way, so they're lying down here. That's why they're always negative imaginary numbers. So let me ask you a question, right? See if you understand what I'm talking about. I know it's a little bit abstract, I know it's a little bit weird, but if inductors are shifted by 90 degrees relative to resistors that way, and if capacitors are shifted 90 degrees relative to resistors that way, then how do you think inductors will be shifted relative to capacitors as far as the current voltage relationship? Well, the angle from here all the way down here is 180 degrees. So if you think about it that way, if you have resistor as your baseline and inductor is shifted 90 degrees this way, meaning voltage and current is shifted with respect to one another this way, and then voltage and current shifted 90 degrees this way, then if you just compared capacitor and inductor, they would be shifted with respect to each other by 180 degrees, and that's exactly what you see. So if you go and you plot on an oscilloscope the voltage and current relationship of a capacitor and compare it to an inductor, then you could see if you look at the voltage and you're looking at the current, it's going to go through and shift all the way to the other side. That's a 180 degree shift. So it's a little bit of extraneous. It's not something you'll probably be tested on, but I know that when I learned it, I was wondering, why are inductors positive imaginary and why are capacitors negative imaginary? And the reason is because the voltage current relationships that we see when we plot the cosines, it kind of trickles into the representation that we use when we use the imaginary numbers. And it shows up into how and where they are on the complex domain. So if I give you and tell you, hey, if I put a component, let's put it this way, if I put a component in a black box and you don't know what it is, you don't know if there's an inductor in there or a capacitor in there, and all I tell you is the impedance of this thing is J5 ohms, positive J5 ohms, then you know it's got to be an inductor, because inductor is always positive imaginary. If I give you another black box and I say the impedance of this thing in this box is negative 3.5 J ohms, right? And that's all you know. You know it's a capacitor. It has to be, all right? But if I give you a black box that has an impedance 3 plus 2J, like maybe I said, hey, here's a black box, 3 plus 2J ohms, because you can represent impedances just like this, real plus imaginary part. In other words, the impedance of whatever's in this other black box has a real part and an imaginary part. The imaginary part happens to be positive, and I asked you what's in the box, then you know. There has to be a resistor in the box because that accounts for the real part. There has to be an inductor in the box because the imaginary part's positive. If you had a negative imaginary part, you know it would be a capacitor. So you can learn a lot by kind of digging around in these little details here. But even though I'm giving you all of these details, and even though all of them I think are cool and important, really, honestly, the only thing you really need to know out of this section and the last section is that in a few sections, we're going to start analyzing circuits. The resistors stay the same. The capacitors, you use an impedance of 1 over j omega c. Use that in terms of an ohm. And for the inductors, you use j omega times L. We replace all the components with our impedances, we do our analysis, and we're done. And you'll see that it's pretty easy. So follow me on to the next section. We'll get a little bit of practice with impedance, and then we'll finally start to solve some real problems, and you'll get some practice with that. Learn anything at mathandscience.com.